This is a tutorial using HZwell preprocessor to build multiple vertical fracs along a long horizontal well. In this picture, you're seeing the grid data, and this shows 3 horizontal wells with multiple orthogonal vertical fracs. This is in the XY plane, so the vertical direction is not seen, but these are vertical fracs, and we are using local grid refinement to model the vertical fracs. This template makes it easy to build the vertical fracs. It's usually recommended that you have a completed model. So a model that is completed in PVT, relative perm, and so on, and all the grid cell parameters have been entered. For example, the cell depths, the porosities, permeabilities, and so on have already been entered. So it's a complete model ready to run, but now we want to introduce the vertical fracs. If you look at the cells in more detail, if I zoom along the path of the well, you can see that the fracture is represented by a very thin column of cells. With the red line here, this is a new parameter, frac KFWF, that shows the cells with a high KFWF number, which is a frac. And it has got 3 cells by 5 cells. So we want to use an odd number of cells for the LGR, so that we can get a central plane of cells that can be used for the fracture itself. So in order to build this, let's go back to an earlier data file where we have the wells, but before adding the local grid refinement. So we use this particular file in the samples folder, and it is horizontal well 10 vertical fracs interlock waterflood before that. We display modified cells, and if we go in and show any parameter, we can see that we would have the 3 lines of horizontal well, 3 lines to 3 horizontal wells. And now we want to go in and use the add hydraulic fracs LGR template, which is found under wells or under edit tables. This is the same menu item in 2 different locations. So this location is easier to access. Add hydraulic fracs LGR, it comes up, and this form appears. So in this form, we can see that we have, in this case, 3 wells. And these well names can be obtained by using drop-down list, well 1, and so on. And this is the time at which the fracs for this well occurred. And this is the time the fracs for this well occurred. And these times can be different. So we can stagger, we can actually use the correct time to modify the cells to get the effective transmissibility of the fracs at the correct time. So before this time, the properties of the LGR cells will stay the same as the original permeability, and only at this time, the frac time, will the time-dependent modifications kick in. For this well here, well 1, we're going to have 10 fracs at this time, and the positions of the fracs are given here, the IJ position, IJ 11, 18. So here is 11, 11, 18. Next one is 15, 18, 15, 18. So we're going to have vertical lines, vertical LGRs created by the program at these positions. So we have 19, 18, 23, 18, and so on. So this gives the IJ position of the frac. The vertical extent is specified by the user. So we can specify in this case here 1 to 3, which is the full vertical extent of this model. But if you got a very thick reservoir, you may want to use a different range of vertical case or whatever circumstance you have, but you have the option to set the vertical range of the frac from K1 from K from to K2. This is a fracture half length, so in this case 100 meters half length on either side of the horizontal valve. The fracture will extend about 100 meters out in either direction of the valve. We specify it here directly, but if we did not specify it directly, if we put it to 0, the program will compute it given the weight of the proppant, the density of the proppant, the width of the fracture. That information can give us the fracture length. So it gives us the extent of how far out the fracture will go out on both sides of the horizontal valve. Then this is the KF, WF fracture conductivity, and we can calculate the conductivity of the fracture given the model fracture width. So the model fracture width is given, we set it, we have to use a realistically sized number, about say 0.5 meters or 0.25 meters or 0.1 meter. We cannot use the actual thin fracture size because it would be too small for the model to simulate. So a reasonable size may be about 0.5 meters for the size of for the width of the LGR cells in the central fracture plane. Given this width and given this KFWF, the model will calculate the transmissibility, the conductivity of that set of cells along the fracture. The direction of the fracs is given in here. Y direction is going, so it's going orthogonal to the X direction valve. The fracs will be in the Y direction. And the number of cells in the X direction, LGR is 3. Number of cells is 5 along this side. So we need an odd number, 3. So the middle number would be for the frac itself. So the middle plane of the LGR cells along the X direction would be the frac itself, and it would extend up vertically in the Y direction for the fracture length that we specified. This is a frac number for a fracture region number if you're doing assisted history matching, regression analysis. And this is a comment column if you want to put some general comments. And the last column is a very useful column. There's 3 options. 0 to build, so in this case we have not built it yet, so it's 0 to build it. After it's built, your model will change, the template will change this to 1, it's done. After it's been done, we can go and add more wells, and this won't be touched, it's been done already. We can add more wells, or we can go in and change other wells and change the status to 2 or 3. So we'll show that afterwards, but this is a very useful column. So now it's set to 0, and let's now go and form modify model and close. So modify model and close. It's going to give us a warning that we should have saved all our data before we do this, because it's going to make major modifications to our data set. It's going to change the number of cells, put in the LGRs, and put in new parameters and modify the time-dependent data. So let's say yes. It's going to go in and process all wells here with the 0 build option. And once it's done that, it's going to promise to reselect the parameter to display. And if we go in and look at the X permeability again, we can see now that it's still the same value, 0.1, so it's not touched the original permeability, but it's created all the fracs for us at the specified positions for the appropriate length. And it's useful to see this new parameter. This is a new parameter, KF/WF parameter, that's created by the fracture template. And this shows us, if we zoom in on it, display zoom in on it, we can see that this is the length of the frac. Just from here to here is the 100 meters calculated for the enhanced permeability. So the permeability itself is not modified, but if you go and just edit tables, time-dependent parameters, we can see in the time-dependent parameters, as you can see the time, at this time, it's going to modify the Y permeability along the length of the frac. It's going to modify from the range of cells, IJK, LGR, IJK, to this range of cells, IJK, LGR, IJK, for a given value. And the Z perm is 100 for the values automatically. But you can change these values if you're doing manual history matching. You can change this to reflect a higher conductivity along the frac or lower conductivity. And this comment here tells you which IJ of that well which you're looking at here. So this time-dependent data is created by the program and is maintained by the program unless you go in and manually change it. So if you want to build a frac and manually change it, you should not rebuild the frac again. But if you rebuild the frac, it's going to modify these numbers automatically for you. So let's close the form, and you can see if we display and zoom, we can see the fracs here. Now if you wanted to remove the fracs for this well, for example, the second well, this is the second well. If you want to remove the fracs, we can go in and say display. Then we can go to wells, HZwell VertFracs, and for the second well, for example, well number 2, we can go in and say to remove the fracs. So this is all one, and now we change to 2. It's going to operate on delete and remove. So it's going to remove these lines. And if you go to 3, if you use 3 here, it's going to delete and keep the line. So it's going to keep the line for us. Control down. So if we did that, we're going to see the fracs removed from well 2 and well 3. And the well 2 lines should be completely removed. So modify model and close. So okay, yes to that. It's going and redo our map for us. And we can see now that the fracs for well 2 have been removed, well 3 has been removed as well. Well 1 is untouched. If you go in one more time, and now HZwell VertFracs, we can see that well 2 is gone, well 3 is still here. And we can reprocess well 3 by changing, for example, the half width. And we can change it to say 150 for the first 5 fracs, 150, and we want to rebuild that by saying this is 0, control down 0. So we're going to rebuild well 3 with a bigger frac in the first 5 fracs. We're going to build that, modify model and close, say yes. And show that again. We can see that well 2 is not frac, well 3 is now refract with a bigger frac in the first 5 frac locations. So this shows the usefulness of the fracture template in building, deleting, rebuilding the LGRs that represent the frac. Thank you for your attention.